In the last video, I went over how to conduct an upper tail hypothesis test using the rejection region method, and we finished up with this picture here showing the critical value, which for a 5% significance level test is the 95th percentile, and then our test statistic in this example lying inside the rejection region to the right of the critical value. And that led us to reject the null hypothesis in favor of the alternative hypothesis. And then I mentioned that there's this p-value here, and that leads to an alternative way of doing a hypothesis test that turns out actually to be easier in the long run. And so let's go through the p-value method for doing the hypothesis test now. So we're going to have the same set of null and alternative hypotheses. Our sampling distribution for the t-statistic is the same, a t-distribution with n-1 degrees of freedom. Our t-distribution looks like a normal curve, but it's a t-curve in this case. And in this case, we are going to think about the tail area beyond the test statistic. And the idea is that if that test statistic isn't too far from zero, then that upper tail area beyond it won't be very small, it'll be relatively large, and that will lead us to being unable to reject the null hypothesis. Whereas, on the other hand, if our test statistic is far out in the upper tail, then the tail area beyond it will be very small, and that will favor the alternative hypothesis. We'll end up rejecting the null hypothesis in that case. So similar question to before, how small would that tail area have to be before we reject the null in favor of the alternative? And that tail area beyond the test statistic for an upper tail test, that's called the p-value. So let's run through how to do that in practice, and if we set the significance level, then that will determine how small the p-value has to be. In particular, if it's smaller than the significance level, we reject the null hypothesis in favor of the alternative, and if it's not smaller than 0, then we fail to reject the null hypothesis. So let's run through our example. Here's the set of null and alternative hypotheses, exactly the same as before. The test statistic, exactly the same as before. Significance level, we'll use 5% again, and then whereas those first three steps are identical to when we did the rejection region method, the fourth step is different because now we have to figure out the value of the p-value to determine whether it's smaller than the significance level or not. So to do that, we could use a t-table, and we could find in the t-table two values in the t-table that are either side of our test statistic. So in this case, if we were to look in a t-table, we would find the value 2.045, which would correspond to the 97.5th percentile, and then we would find the value 2.462, that would correspond to the 99th percentile. And those are the two values that are either side of our test statistic, which is 2.40. The p-value, remember, is the tail area beyond the test statistic, and so the tail areas beyond each of these two values will bound the p-value. Okay, one will be a little bit bigger, one will be a little bit smaller. So in particular, the tail area corresponding to 2.045 is 0.025, and the tail area corresponding to 2.462 is 0.01. And so because the t-statistic is in between these two numbers, the p-value must be in between 0.025 and 0.01. So that's how to find an interval for the p-value using a t-table, it's actually much easier just to use statistical software and get it directly. So we can use the pt function in R and find out that the p-value is equal to 0.0115196. To make the decision, it's actually good enough to get a range on the p-value, because all we have to determine is whether our p-value is less than our significance level. And so if the entire range that we've found is less than 0.05, which it is in this case, then we reject the null in favor of the alternative. If we are able to get the p-value exactly, then we can just look at that number and ask ourselves if it's less than the significance level, which it is in this case. So we reject the null in favor of the alternative, and then again, as we did before, we have to end with a concluding statement that relates back to what we were trying to find out in the first place. So in this case, our sample data suggests that a population mean greater than $255,000 is more plausible at a 5% significance level. That's because we rejected this null in favor of this alternative, that the population mean is bigger than 255. So here's that picture again. So now we can see what we mean by the p-value. It's the tail area beyond the test statistic. And if our test statistic is in the rejection region beyond the critical value, our p-value, which is this tail area, okay, the double hashed piece, is clearly smaller than the significance level, which is the single hashed piece, okay, all the way out to the tail. So that's an example of an upper tail test where we reject the null hypothesis. Test statistic in the rejection region, p-value smaller than the significance level. How would the picture change if we were to fail to reject the null hypothesis? The critical value would stay where it was, and the significance level would be the same size as it was before. But now our test statistic is not in the rejection region, it's on the left-hand side of the critical value, and our p-value, it's bigger than our significance level because it's as much area as the significance level and then plus a little bit more. So this would be how the picture would change if we were to fail to reject the null for an upper tail test. Lower tail tests are similar, only all the actions in the lower tail. So here's a picture of rejecting the null, where our test statistic is less than our critical value. It's in the rejection region because the rejection region is in the left tail now, everything less than the critical value. And our p-value is that tail area to the left of the test statistic. That's clearly smaller than the tail area to the left of the critical value, which is our significance level. Here's an example of a lower tail test where we fail to reject the null hypothesis. Critical value is in the same place, but our test statistic now is not in the rejection region, and our significance level is up to here, but our p-value is all the way up to here, and so it's clearly bigger than the significance level. Two-tail tests operate in both tails, so now our rejection region is in two places, to the right of the critical value in the upper tail and to the left of the negative of the critical value in the lower tail. And any test statistic either in the rejection region up here or the rejection region down here would allow us to reject the null hypothesis in favor of the alternative. The significance level, we divide that between the two tails, so half of the significance level would go up here, half would go down here. So let's say significance level 5%, we would have 2.5% in the upper tail and 2.5% in the lower tail. And similarly, our p-value gets divided. Half of it is up here in the upper tail, half of it is down here in the lower tail. And so clearly still, if the test statistic is in the rejection region, the p-value is going to be smaller than the significance level. And finally, here's how the picture changes if we fail to reject the null hypothesis. Now our test statistic is not in the rejection region, either in the upper tail or the lower tail, and our significance level is only up to here on both sides, whereas the p-value is all the way up to here on both sides, and so the p-value is clearly bigger than the significance level. So that's how to do a hypothesis test using the p-value method. Let's think now about 4 possible hypothesis test outcomes, because we're making a decision to either reject the null hypothesis in favor of the alternative or failing to reject the null hypothesis. The reality is either that the null hypothesis is true or it's not true. So if the null hypothesis is true and we fail to reject it, then that's a correct decision. So that would be a good outcome. But if the reality is that the null hypothesis is true, but we actually reject it because we get a test statistic in the rejection region, or because we get a p-value smaller than the significance level, then we'll have made a mistake. And that's called a type 1 error. Rejecting the null hypothesis when it's actually true. And there's a probability of that happening every time you do a hypothesis test, and that probability is set by the significance level. Okay, and so that's typically why we set the significance level fairly low, say 5%, because we want that probability of making a type 1 error to be unlikely. We want that probability to be low. What if the null hypothesis is false, though? Okay, if the null hypothesis is false, but we don't reject it, then again we've made an error. And this is called a type 2 error. And we don't get to directly control the type 2 error, but we do get to control it indirectly. And unfortunately, as the probability of the type 1 error goes down, the probability of a type 2 error goes up. And so when we set the significance level, the probability of a type 1 error, we can set it low, but we can't set it too low, because otherwise the probability of a type 2 error goes up. So we have to strike a balance. And then finally, if the null hypothesis is false, but we reject it, or rather, and we reject it, then that's good. We've made a correct decision. Okay, so probability of a type 1 error is the significance level. That's what we get to set. If we set it too low, though, we can increase the chance of a type 2 error occurring. And so there's a trade-off there. And so 5% is a pretty good balance. In some fields, you'll see 1% or maybe 10%. Other ways of reducing the chance of a type 2 error is having n as large as possible. So large sample sizes are good, and then also making sure that you're using sound statistical methods. So we should always keep in mind that we can make errors when we do hypothesis tests, and so you do want to do them judiciously. You want to decide what your research question is and then set up your hypothesis tests before you even collect data, and then when you collect the data you can run the hypothesis tests that you've decided on ahead of time. But you always want to keep in mind that you may end up making a mistake. So in this video I've gone through the p-value method for doing hypothesis tests, and it turns out that this is the method that we'll use more often moving forwards, because we can often get statistical software to give us a p-value, and then all we have to do is decide if the p-value is smaller than the significance level, which we typically would set at 5%, and if it is, we reject the null hypothesis in favor of the alternative hypothesis, and if that's not the case, then we fail to reject the null hypothesis.